put this lowercase.
So, today we're going to get started, and after y'all's great comments, I kind of realized some of us are stuck in different parts. So one of the first questions was a couple people didn't understand how Gibbs sampling and what we talked about on Friday makes your models really connected. So we're going to take a couple steps back to go forward, and I'm going to try and address all of y'all's questions that you guys wrote. Thank you for doing that. It really helped me set up today. So let's talk about Gibbs sampling. Let's say, also, if my handwriting starts to shrink, let me know. I'm used to, like, my handwriting is microscopic on paper, so writing big's pretty hard. So if it starts to shrink, yell at me. So we're going to say we're going to let xi's come from a normal mu phi, which is equal to 1 over sigma squared. We've seen this before. Okay? Our goal here is to learn mu and phi. Because in practice, we're given data, and normally as statisticians, our job is to figure out these parameters that tell us about our population, right? So, our goal is to learn this. We've already established the likelihood, condition of data, proportional solution. It should all look familiar. I'm just writing it out so that we are all on the same page. Likelihood. Our priors are mu and prior on phi. We're all good here, right? Just a little review, always helpful. Then our posterior, so pi, mu, given all of our data, is right here. X, oh, yeah, right there. It's 1, it's 2, all the way to xn. Proportional to we're good, right? Everyone following? Seen this before? Yes.
Just with regard to the priors on mu and phi, like we've decided those, right? Or
I'm telling you, we're going to use our reference Jeffrey priors.
okay.
We could end up doing normals and gammas, but then we have other hyperparameters, and how do we choose those hyperparameters? So I'm going to keep the problem a little bit simple, and we're just going to go with these today. Is that cool? Awesome. So our goal is to learn this mu and this phi. When we were first originally learning about this problem, Dr. Lehman gave us this phi, or he gave us mu, and he was like, figure out the other distribution. Okay? And so what we would do is if phi was known, all we would have to do is sample mu. So let's say phi is known, mu. We know this distribution is going to be a normal x bar, not sigma squared, phi over n. We're giving you phi. We will be able to find mu. This is the full conditional for mu. Okay? Now, let's say we don't know phi, but I'm going to give you mu. Giving you mu, we want to find the full conditional on phi. We know what this is as well. We know it's a gamma. So given the other parameters, we know the distribution of the other one. Given phi, we know the distribution of mu. Given mu, we know the conditional distribution of phi. Okay? In Dr. Lehman's lecture, he took it a step further and said, let's pretend we don't even know how to sample from a normal. And he did a Metropolis-Hastings type of algorithm. I'm going to show you an easier way, which will help us connect to mixture models. We all know how to sample from a normal, and we all know how to sample from a gamma. So in our code to run this, it is literally 4 lines, give or take. Okay? So I'm going to just show you some code. But all we're doing for our Gibbs sampling is for some t, number of iterations, 1 to a big T, we will simulate through this, where we're going to find our new t, given our old. Now we're going to find our new phi, given that. And so at mu equals 0, we have to initialize, of course. We can initialize it to be some number, and phi to be some number. I know that's starting to mush on top of each other. But given the original phi, we're going to plug it in here, we're going to get a sample. That's going to be our new mu. Then we're going to keep going through this. So I'm going to show you code because that's potentially the easiest way to see some of this stuff. Bless you. Let's make this bigger. Okay, so we're going to perform the Gibbs sampler. So n is our number of observations. I just said 40. We're going to have a true mu of 31, because I love the number 31. And then we're going to have a sigma, so the standard deviation is 3. So our phi, a true phi, is actually 1 divided by sigma true squared. Okay? So for MATLAB, putting it into the randomly generated and normal, you need the sigma or the standard deviation. Every code's different. So what we're going to have here, I'm just going to generate some data. And it's going to look like that. Oh, awkward. Just ruined the surprise. Okay, hold on. Things are being mounted. There we go. Woo! So this is what we would see. Your collaborator comes into you and he gives you this data and they're like, I want to figure out the mu and the variance of this single normal. The Gibbs sampling algorithm, we're going to iterate 1,000 times. Okay, first step, we're going to initialize mu and phi. I initialize them pretty far away, so mu originally is 0 and phi is 1. Here is the entire Gibbs sample. We're going to generate from a normal using the mean, and then this is the, again, we're putting in standard deviation, so I do a little bit of transformation stuff, but it's going to be this mean and this variance. Okay, sample from that, store it, then the phi, we're sampling from our gamma, and that's it. And then I'm just going to plot some trace plots. So let's run this. And boom. Here's the mu trace plot. So number of iterations, then we have mu. We can see it converges at 31. And then here's our phi. This is the right phi after putting it in. Here's that joint trace plot that Dr. Lehman showed us. With using just Gibbs sampling and not that Metropolis-Hastings within, we converge really, really fast. And this is what Dr. Lehman was talking about, okay? So Gibbs sampling, all it is doing an iterative process over the full conditions. Everyone good with that? Any questions? This is probably also a homework question. Okay? So now that we have an idea of, just remind you guys what Gibbs sampling is. Let's go back to our mixture example. Also, homework 3 is due Friday, October 25th, and then there will be 2 review sessions, Wednesday and Thursday. Good?
Any idea if there can be an extension for the homework? Because it's kind of impossible to finish it on Friday, I guess.
What?
I have no power over that because I'm not the true professor.
Okay.
So that's a Dr. Lehman question. Sound good? All right. So here, this is assuming we have one normal. Now, let's assume our xi comes from this. I don't use sigma squareds, I'll use phi's for you guys. Phi? Phi. Okay? So, also, pi 1 plus pi 2 have to sum up to 1. Because pi 1 and pi 2 are like flipping a coin, and then you're going to sample from cluster 1 if you sample from the first component, and you're sampling from the second component if you flip a 2. Okay? These right here, this 1, 1, and these 2's are representing the groups. So this group 1, group 2. Okay? Now, we want to get something that looks like our Gibbs sample over there, but we have this extra layer of community assignments. So each of these xi's are going to have a community assignment, which we're going to denote as CI, which represents the cluster assignment for the ith observation. Okay? So if we have something that says C5 equals 2, the 5th observation is in the second component. We all good with that notation? Okay? Now C, this is a lowercase c. C can be between 1, 2, ... uppercase c, which I'm going to denote with these extra things. So in our case, we only have 2 groups, so uppercase C, also denoted by these lines, is 2. Okay? Cool. Awesome. Now the question is let's say, nope, we're not there yet. Let's define what our goal is first. Our goal would be to estimate or infer mu1, phi1, mu2, phi2, and the community assignments for each of the xi's. So goal, learn mu1, mu2, phi1, phi2, and then the community assignments. We good there? Okay? Now, I'm going to assume something. I'm going to erase this. you guys. If given all CIs, the community assignments, could you infer U1, U2, V1, oh, that's not, V2.
Yes.
Yes. It's as simple as, if you are still struggling, it's as simple as saying here's x1, x2, x3, x4, x5, x6. Here's group 1. Here's group 2. I told you the assignments. I told you these are group 1, and I told you group 2. How would you infer it? Say that again. Say it again.
We can run a Gibbs sampler.
Gibbs sampler. So we would be running a Gibbs sampler here. So we would have N1 would be 3. So this is the number of observations in group 1. So using this data, we would run that Gibbs sampler. So mu1 conditioned on v1 and x would come from a normal x bar, where this x bar, I'm gonna have to write bigger, I already know. N1. So these xi's are only from this group. We're dividing by the sum, okay? Good? And again, phi inverse and inverse. Could probably write that nicer, but I didn't. Then your phi1 would be coming from a gamma n1 over 2. Over here in this more general problem, we have n, but now we're only in group 1, so we're only going to have n1 points, and we're going to do over the sum. Mu1 squared over 2, where these xi's are only coming from group 1. For group 2, yes?
Excuse me, the n next to v shouldn't be n1.
Absolutely. Sorry. Fantastic job. Thank you for keeping me on track. Okay? Now, for group 2, we do the same thing, but these n1s turn to n2s, and our xi's are only from group 2. So given the cluster assignments, we know how to infer. Everyone good there? Any questions? Cool. Oh, I don't want to erase that either. Now, okay, we're going to erase this. It's just going to happen. Question 2. If given mu1, mu2, v1, v2, could you tell me, let me see how I exactly phrase this question. Could you place probability of being in a particular cluster? Okay, so we're going to change, oh nope, I'm going to draw a new picture. We're going to keep erasing over here. So we have the same line, but now what I'm telling you is this distribution, group 1, has this mean, and it has this phi value. Group 2 has that and that phi level. Could you, given your mu's, tell us a probability of being in cluster 1 and cluster 2?
Yes.
The probability, or even maximum likelihood estimation.
So that, doing a maximum likelihood estimation is a different technique to find the cluster groups, which is called expectation maximization.
EM.
Yeah, correct, awesome. So what we're trying to do here is, think about if I had this x1 right here, and I gave you mu and phi, and I told you it was a normal, and a computer, could you find that point? We're finding the probability of being this on this distribution. In a computer, you probably would write it as like d norm, the density at that point. Does that make sense? Yes? No?
Yes.
Okay, got some yes. I'll take it. Okay? So what's going to happen for this xi in computer world, you're going to do d norm of mu1 phi1 of our x. Okay? That's the probability of being in this cluster. You would also then d norm of, given mu2 phi2 of x1. You're going to find the probability that x1 is in the second group. From this picture, you're going to see it's pretty low. Then, for each one of these probabilities, because we need it to sum up to 1, you're going to do the sum of the d norms. Okay? The reason you're summing is you're normalizing. To put it between 0 and 1. Does that make sense? Now, we have a mathematical way of writing this down using Bayes' rule. Let's look at that. So the probability that xi is in C, that's baby C, which means it could be 1 or 2 in our case, conditioned on mu1, mu2, phi1, phi2. Okay? Bayes' theorem tells us we can also write it condition of xi, our 1 point, and our cluster, times our a priori belief. I'm going to talk about this in 1 second. Let me just finish up.
Yeah, excuse me, shouldn't the probability upwards be also knowing C, I?
So what we're doing is
It's
this.
I in C, but shouldn't it be knowing CI or at least knowing cap C?
So what we're going to do is very similar to this equation. So we're going to say the probability of xi in C1, when C equals 1. So the probability that xi is in that first community. Okay? And we're going to find that. And then we're also going to find the probability that xi is in the second community.
Yeah, so C is not a random variable here, it's a constant.
No, it's not. So, I see what you're saying. Condition that we know there's 1, 2, 3 communities. Fair enough. Absolutely. Cool. Is that good? So, given these guys, this is Bayes' theorem. Then, we're going to add our normalizing constant, which is what this is doing is the same thing as this idea. Find the probability it's in one cluster, find the probability of the other, and you're just going to normalize over it. This is just fancier, weirder notation. The question is, right here is our A priori on sample from each cluster. So this pi c is very similar, I erased it, to our pi mu is proportional to 1, or pi phi is proportional to phi over 1. What we can do is basically take this, our a priori, and say it's equivalent. Now, that's probably the best one. It is, our a priori, would it be fair, question, to say, prior to seeing the data, we would assume that each group would be sampled equally. Okay, so our a priori, in this case, is 1 over big cap C, which in our case is 2. If you look super closely, this pi c and this pi c will end up canceling out with our form. Does that make sense? Because it's going to be 1/2, you can pull this 1/2 out, they're canceling out. So it's not that big of an issue with how we are working on it right now. You can end up making this more fancy, but let's not worry about that yet. Okay? So, big take-home point. If given C's, we can sample our mu's and B's, right? If given our P's, we can sample our C's, right? That's all a Gibbs sampler is doing. So now we just have to iterate over that. Okay? So, I'm gonna erase this chart. So our Gibbs sampler for mixtures is for some t. Again, this t, big. What do I mean by big? It depends on your dimensionality, depends on your number of clusters. Higher dimension, higher clusters, you're gonna have to iterate longer. Lower, probably not as long unless you have a really complex model, okay? What we're gonna do, we're gonna have mu c, and we're gonna initialize at some number, where mu c represents the mu for the C cluster. Good with that? Phi C is going to represent the phi for the C cluster. Okay? What we're going to do, probability that xi is in C given mu c, phi c. And that we know how many clusters there are. Okay? But this is for each xi. So really, what it's going to be is for each of the i's, 1 to n. Someone told me that that would probably help clear up some notation. So for each of the xi's, we're finding the cluster and we're trying to put a probability on which side, what cluster it's on. Okay? For each of those xi's. This is finding, this is given t minus 1, t minus 1. Given mu c and phi c, we're finding the clusters. We're what point?
So I think that we loop over I equals 1 to n, and also loop the class from 1 to 2.
Yes. So for this point here, we're going to see if it's in cluster 1 or cluster 2.
Yeah. So
That's giving us a probability.
So in the loop from I equals to 1 to n, we do another loop for class 1 and 2, right? And then compare the probability.
Thinking about, yes, you could do that. There is a more savvy way to do it in a computer, so you're not doing for loop. But yes, you have to make sure you're doing both of the clusters. And as we get more clusters, you have to do more and more clusters. But yes, in a sense, you would be looping over the clusters as well. Is that good?
So in this step, we assign the class to the x.
Yes. So this step, given our mu's and given our phi's, we're going to say x1 is part of cluster 1, x2 is part of cluster 2, x3 is part of cluster 2. And we're going to get a very long list of what the clusters are, the assignment for each of the x's. Does that make sense? Awesome. Cool.
So you re-update that every single
Yeah.
you look through your time?
Yeah, but
Okay.
yep. Great observation. So now we found our C's, okay? And I erased it because the score is really big. But now we're given the community assignments. All we have to do, find mu of C, condition on and the data and the cluster assignments. Just from normal. And these parameters will change based on what cluster you're in. So, not going to worry about writing that in. And this will be from a gamma. Which again is going to depend on if you're in cluster 1 or cluster 2. It's going to change the number and the data set. Does that make sense? Okay, and then n. So what you're doing is Gibbs sampling is you're just conditioning. Given this parameter, you're going to condition on everything else. And we know the sampling distributions. And we're just going to iterate over this for a lot of t's. Any questions at this point? Speak louder.
Okay. So last week you mentioned like flipping a coin. So like which step is it like incorporating the coin flip?
Fantastic question, Quinn. Seriously, that was a great question. So here, how I see it and how I code it up in my problems, I'm going to erase this if you guys don't mind, is you're iterating through each xi. So you're going to have the probability prob of x1 in cluster 1, the prob of x1 in cluster 2. You're going to have a really big matrix. It's going to be n. Does that look like an n? And then you're going to have c columns. This is how I see it. And so right here for x1, all we did was get the probability that it's in cluster 1 or cluster 2. We didn't necessarily assign it. So that's where we're going to do our coin flip. So we find the probabilities of it being in the cluster, and then we flip it. Because if we look at something like this, these two distributions are pretty spread apart. And so if you're here, and it's telling you you're in, this will probably say you're in cluster 1.99, and the probability of you being in cluster 2 being x1 is probably 0.01. You flip that coin, you're going to be told you're in here. But let's say our distributions overlap a little bit. And our point, x whatever, is here. It's going to be a little bit harder, so you're going to flip that coin. We're doing a more probabilistic way of doing this, and through the literature they call this soft clustering, where if you do something like k-means, that's hard clustering, saying it is in this group or it's in this group. We're putting more of a probability on it, and we're kind of flipping the coin. Does that make sense, Quinn? Does that answer your question?
So, to that end, are we actually doing that here, like between the embedded for loop and the next step?
It would
are we
be
assigning those?
in this step, essentially. It's through this step. So if you want, we can even say you can do you're gonna do a coin flip here. Based on it. Does that make sense?
But is that mandatory? So if you do, hard clustering instead of soft clustering, so the probability with the highest probability, you just set the assignment. Would that be kind of biased at the end of the day or no?
So your question, let me just make sure I understand. You're saying we create these probabilities and then you're like, well, this one's higher, go here. My question for you, what if it's 50-50?
And you can, just like Kay, you were saying that there are two types of clustering, soft clustering and hard
Yes.
clustering. So if you do run this algorithm according to hard clustering, how would that impact it?
You wouldn't be doing this via hard clustering. Because for Bayesians, or making a probabilistic model, you wouldn't be doing this as a hard cluster.
Okay.
Does that make sense? Any other questions?
So we are doing a coin flip with respect to the probability of what of xi belongs to group 1 or group 2.
Yes. So it's, we have a coin. You don't have a coin? No? Okay. So heads or tails, right? I'm gonna flip a coin. In our simple case, if it's heads, we're gonna say we're in group 1. If it's tails, we're in group 2.
But then what's the meaning of calculate?
It's a biased coin, it's not a...
It's not the 50-50% coin, it's like the different probabilities.
So let's say we have 3 clusters, and we have a 3-headed sided coin. I don't know if that's even possible, but we have a 3-headed sided coin, head, middle, tail. We flip with some probability that x1 is in cluster 1, cluster 2, cluster 3. Flip it, tells us we're in cluster 1. Flip it again, it could tell us we're in cluster 2. So if we take this point right here, do you think we have a higher probability of being in cluster 1 or cluster 2? Boom. So let's say the probability of x1 being in cluster 1 is 0.99, yeah, 0.99. The probability of x1 being in cluster 2 is 0.01. Simplifying some math, you have to do this, of course, to get those probabilities. But when you flip that coin, you're going to already have a higher chance that this x1 is in that group. So you're flipping that coin based on the probability. You are saying you know these mu's. It's a hard concept, without a doubt. I struggled with this when I first was learning it. Does that help clear some things up? Cool. So let's just go back to our sims, because sims are cool.
So Eric, can I ask a question?
Absolutely.
So why, after we do our cluster assignments, why can't we just use like an MLE as opposed to drawing from like this here? If we just said like the mean of group 1 is just the mean of all the groups.
So your question is, instead of doing a Gibbs sampler, why not just say, here's our data, take X bar, and take the variance, right?
Yeah, and then rerun it with the new cluster assignments, and then you'll get new, cluster assignments, and then you'll get new means, and then you'll run it again. And keep running.
I think that'd be a valid reason. I think it would be a different sampling.
I think you wouldn't get
But-
as much like movement.
Let me think.
Yeah, it definitely wouldn't move as much because you wouldn't be randomly sampling down there, but you still have
Yeah.
random cluster assignments, which would still move you around the space.
Yeah, it'd be a lot less. I feel like it would be like tinier steps, which
So,
could be good, but
I don't think that's a wrong approach, but I'm gonna say this is a simple case. And so the reason I'm saying it's a simple case is it's a normal and a gamma only working with 2 clusters. If you start getting in higher dimensions and things are not as simple as this, you might end up getting stuck. Where with this, you can do a proposal and maybe start moving a little bit more, kind of like Annie's saying. Is that a bad, I'm gonna be straight up. I don't think it's a bad idea, but I think it might cause some issues when we go higher dimension. Annie?
I think it's the same thing as saying, oh, let me just take the probability that's the highest, right? Like, oh, let me just take the estimator that's the max of the posterior. You're taking out that probabilistic component.
So I think what he's saying is keep the whole, don't want to put words in your mouth, Ryan. He's saying do that coin flip, but once we have the community assignments, we just take the mean and the variance.
Yeah, I think it's similar.
Without having this more Bayesian approach. I think it's kind of a mixture of Bayesian and frequentist in a sense. And I don't know if that's right or wrong. I'm gonna be straight up with you guys.
Expect that's like k-means, except you're using Hellenovus distance instead of the Euclidean distance, right?
I say something about
There's
that.
still a probabilistic coin flips, right?
Yeah, so
K-means
you,
wouldn't have
what,
like coin
what
flip.
Yeah, but
Ryan's
there's
trying to
no
say
probability in
is
the
he would
sample.
keep this part, but instead of maybe running a Bayesian approach here, he's just saying, we're given this data, why not take the mean and just take the variance without having this Bayesian spot. A potential issue is that our priors right now do help us be a more frequentist on the conditional sense. But if we want to put more weight and have our priors be a little more difficult, or not difficult, different, then it would change our assumptions. So that'd be a really cool question to look into and really see the true difference. That's a good question. Ben, do you have a question?
I was going to comment also something about the fact that this looks like a k-means algorithm with a different measure for distance.
Yep. And so there's also expectation maximization. One day I'll be able to say that without stuttering. K-means, these are all just different clustering algorithms. Okay? You guys want to see some sims? We saw them last class, but do some reading. Is this at least clearing things up since Friday? Putting Gibbs and mixture models, any questions? Oh, wrong password. Gibbs. Yep. So we're gonna simulate our data. Here's our cluster. Let's get this bad boy running. So this is our data set. That's not the data set. Well, we're gonna see what happens. Our pies are very low for this one. I have another picture. I'm on the struggle bus. It's okay. But with this pi 0.3 being low, the number of iterations I did aren't enough. Yes, Annie?
When you code this up, do you typically store all of your C estimates for each time? Is there a benefit to that?
I normally don't. So this is my code. Let me see if I can make it a little bit smaller. So I apply. Get rid of that. So I go to the sampling C Gibbs, which is another function. And that won't open. And this one's crashed today.
Let's function you design the sampling CDs.
Mm-hmm. So pretty much rather than having, I like being very organized, and rather than just having code everywhere, I like to go to this function, sample the C's, it outputs it, and then throw it in. And it looks like MATLAB's crashing. Oh. Okay, cool. So this is the C's. I don't store them, but pretty much sampling from a multivariate and then normalizing. It's all my C is doing. A little bit fancier stuff, but because I had to make it more robust. So again, of course, the data. This was the data. We have less data here than here. So already we can probably think that our estimates for this one might not be as good. And I'm also running it for a shorter amount of time because or in class, and I don't have a while. So we can see that the second cluster, which is orange, is a little bit more crazier, and if I did let it run in longer, it would eventually converge, but mu 1 looks really good. Okay? We make this even. We run. And run this. And after this, I will let you guys go, but I'm gonna ask another question. Same active learning strategy. My friends in the pilot class know. Again, write anything you're confused about, what you want clarification. I can also give these to Lehman and be like, this is where, what's making sense, what's not making sense. And Lehman will be back Wednesday, lecturing about probably, don't quote me on this, numerical issues of Gibbs sampling and metropolis. Sound good?
I'll be alright.
Everyone happy? Homework's due Friday.
You can share, please, and
At least started, because I don't know if they'll give an extension.
I'm good.
And review sessions Wednesday and Thursday. Sound good? So if you want to stay to watch this, awesome. If not, I hope you guys have a good Monday and go do something fun.